Okay, so I want to start looking at related rates, and the key here, and maybe it's subtle, maybe it's not. Is rates. Rate means how things are changing with time, and so it seems appropriate that we started doing derivatives with parametrics, which deal with time, and so related rates. We're also going to look at things changing over time. But these related rates, they're called related rates because there's some kind of relationship that's going to exist that's changing, right? So this idea of related rates is that you have some relationship, and how is it changing over time? And I mean, some of the examples that we'll look at first are very kind of like elementary, right? Very arbitrary or contrived, so they come out nicely. But the point is that any kind of relationship that exists, if you start analyzing how those different pieces change over time, that's really what calculus is examining, these changes of time. And like if you want to examine instantaneous rates of time, instantaneous rates of changes in time, and then that's where really the derivative comes into play. So it's very applicable to many fields in science, like engineering, physics, things like that. But very simple things to start with. Okay, a pebble is dropped into the pond, creating circular ripples, right? So and I'm sure it's dropped, and then the waves go out, right? I've probably seen that before, I'm hoping. Okay, so anyway. It does give us some things about what's happening here. It says that the radius of the ripple is increasing at a rate, look at that, at a rate of 2 inches per second. And I know, again, subtle, but emphasizing that they are giving us a label that's in terms of a rate. And we're going to have to make sure we answer questions appropriately with the right labels. Are they quantities? Are they rates? Are they measurements? Is it time? So that rate's important. And then it says at what rate is the circle's area increasing when the radius is exactly 10 inches. Okay, so the first thing we need is the relationship. Okay, what's happening here? It says the radius of the ripple is increasing. Now these are circles, right? So the radius is increasing, and these are circles. So there must be some relationship that exists between a circle and a radius, right? And so, well, there's two I can think of right off the top of my head. Every circumference of a circle is 2 pi times the radius, and every area of a circle is pi times radius squared. So how do you decide which relationship to pick? Well, it kind of tells you in the problem, right? Circle's area. So I'm going to think about the circle as an area formula is equal to pi r squared. That's the relationship, okay? So what I'm going to do to that is introduce a derivative, and the derivative is going to be with respect to time. So what I'm going to do is I'm going to take that relationship, and I'm going to take the derivative with respect to time, because that's going to introduce time as a rate. So on the left, it's just 1, but then since that's not a time, it's 1, and then it's immediately multiplied by dA dt. Right? Now, if you want to keep that 1 there, you can, right? You don't have to, and I usually don't. Okay, and then equals. Now here, remember, pi is just a coefficient. The function is r squared, so anything squared, the 2 comes down, so it's 2 pi r to the first power, and immediately we multiply by dr dt. So I want to emphasize, again, both of those quantities. This quantity is a rate, and this quantity is a rate. And if you keep the numerators, organized, that this side is the rate the area is changing with respect to time, and this is the rate that the radius is changing with respect to time. So now I have a starting relationship that now has introduced the element of time. So it says the radius of the ripple is increasing at a rate of 2 inches per second. Well, that rate can be substituted somewhere here, and since it's the rate of the radius, guess what? We could put it right there, right? So we can put the 2 right there as a quantity. So now I know that's a 2, and it's saying at what rate is the circle's area increasing when the radius is exactly 10 inches. So we know that's 10, and we know that's 2 pi, and we're trying to find dA dt, which is exactly the missing piece. So if I multiply that 2 pi times 10 times 2, that's going to give me 40 pi, and we've got to represent dA dt with what it's measuring. It's the rate area is changing with respect to time. So that would be inches squared, because area, per second. Now, one thing that I want to give a shout out to Mrs. Olisar, she does a really nice job of this, is she emphasizes labels. So if you go back over here and say, okay, 2 pi was my constant, but what did 10 represent? 10 represented inches at that moment. What did 2 represent? 2 represented inches per second. So if you actually put labels in appropriately, do you also see how you're going to get inches squared per second? Which is pretty cool. Okay, so you won't always be given, and most times you won't be given that equation that you have to take the derivative of. So you have to kind of read the context of the problem. So let's do another one here, just in this video here. Let's see. It says all edges of a cube are expanding at a rate of 5 centimeters per second. How fast is the volume changing when each edge is 10 centimeters? So and I don't know if I stressed this on the first example, this 10 centimeters, that's like a snapshot, a moment in time. Like things are changing dynamically, fluidly, but if you could somehow just take a picture, right? Take a screenshot, right? I was going to say take a selfie, but no. Okay, take that shot. What's happening at that instant? That's when that 10 is used for. It kind of reminds me when you did like limit definition of derivative and then plugged in a value as a snapshot, right? Like as a one moment. So let's start with volume of a cube. So volume equals side cubed, right? They're all the same side. So side cubed. And then, right, so you have this cube. And then you're going to start expanding it. I wonder if I could do this. Ta-da! Oh my gosh. Okay. That's awesome. Sorry. So your cube is expanding. Oh my gosh. I just amused myself. This is great. What a great day. So it's expanding and I want to know what's happening at one instant. So if I could somehow take a screenshot of that and know what's happening. So before we get to that dynamic part, we have to introduce the element of time. So we're going to try to take the derivative with respect to time on both sides. There's the pen. I wanted to choose like that nice green color. Okay, so we're going to ddt both sides. I don't know if that's like a verb, but it is today. We're going to ddt it. So the derivative of velocity, that v is just 1, but then we're going to immediately multiply by dv dt. And you need this, dv dt. I know Mrs. Moore stresses it, and I'm going to stress it because they look for it on the AP exam. Okay, so dv dt equals, and then this is a cubic, so it's 3s, you can't change what that is, squared, but then immediately multiply by ds dt. So we have two rates. How are things related, right? How is the volume changing with respect to time? Well, it's 3 times side squared times the rate the side is changing with respect to time. Okay, all edges of the cube are expanding, so getting larger at a rate of 5 centimeters per second. So that 5 centimeters per second is the rate the sides are expanding. So I could put that there. So that's 5. And if you want to call it centimeters per second, you could. We're looking for a particular moment of time at 10 centimeters. So it's 3 times 10 centimeters squared. And that'll give us the rate the volume is changing, right? How fast is the volume changing? And I left the labels here. So when I square 10, I get 100, but then a centimeter squared. 100 times 3 is 300. 300 times 5 is 1500. But I've got square centimeters times a centimeter, so cubic centimeters per second. And that would be a great label for volume changing with respect to time, right? Volume changing with respect to time. Okay, so I'm really still excited about that. That was really cool. Sorry. So those are the first two examples for related rates. And, it's not a hard concept once you know what the equation is. But that also makes it the hard concept because you don't always know what that equation is. You have to do a little bit of context, reading to get that equation. Okay, very nice job. We'll do another video with another couple of examples just to kind of keep our bearings on related rates.